Hello, my name's Tom. This is an extruder that I'm really excited about. It's called a VDE100. Here's a close-up of it. This is the invention of RQ3. Now, I've linked to some of his material below. This extruder is tiny, it's really light, and it has a high gearing ratio. So it can work with a small motor, light print head, faster print speed, and also with really low current, which means you don't have to worry about the motor getting hot and melting the filament and all that kind of thing. It's what I've been wanting in an extruder. However, I got this one from RQ3, and it's lovely, but it's made of very high-grade components, CNC machine carrier, and not so easy to source screws and so on. This is my equivalent, which I've made at home. Here's a close-up of my one. And I've made this one at home with really low-grade equipment. This is my primitive and minimalist set of tools. A power drill with, unfortunately, quite a lot of run-out on the chuck, so it's not great for the finest quality work. It wobbles a bit as it rotates. A drill press. Not a drill press. A drill stand, which is also kind of wobbly. A sanding disc, which mounts on the drill. If you don't have a sanding disc, you can make your own. Here's one I 3D printed. 5mm drill. Insulation tape. 45-degree set square. Calipers. And a screwdriver. Oh, and not to mention a 3D printer, which I count as minimalist because every good home should have one. And these are the raw components. PLA filament, orange, is a blatant copy of Prusa. Sorry, did I say that out loud? In honor of Prusa, 3 small bearings and 3 M3 screws. This video is about how to make one of my version of the VD100 extruder. And I'll get to that later. I'll put some timings below, so you can jump straight to that if you want. But first, I think it would be helpful if I talked for a few minutes about the original VDE100 itself, how it's built and how it works. Going back to that close-up picture, you can see how the VDE is constructed. It has 3 bearings mounted on a carrier. The bearings are at an inclined plane, inclined by 15 degrees. The axis of each bearing is 15 degrees inclined to the direction of the filament. And this makes it a rotary extruder. It rotates around the filament, which feeds through the center of it. It's mounted on a motor, which has a hole drilled down the center of the shaft, about a 2mm hole. And you feed the filament into the actual shaft, and it feeds through, and the extruder is mounted on the shaft, and because those bearings are inclined, one of them has a sharp edge all the way around it, a knife edge, and the experience of the filament is that feels like the thread of a nut. As it rotates, it catches the filament and it cuts a helical thread. Looks like this. And it also moves up and down that helical thread. As you can see, the filament is coming out very much in the same way that a bolt will move up and down a nut. If you rotate the nut, the bolt moves with respect to the nut. And the same thing happens with the filament. I mentioned earlier the gearing ratio of this extruder. For one rotation of the motor, it drives a lot less filament through than an extruder based on something like Bond-Tech gears. And the amount it drives through is dependent on the angle of inclination of the 3 bearings. But the consequence of this is that the number of steps per millimeter is a lot higher. And I was finding with my not particularly fancy motor, it's a second-hand motor I got out of an old Epson printer, the progression from one step to another wasn't perfectly smooth, and this resulted in artifacts in my print. By having a lot more steps per millimeter, those artifacts go away. And I'd experimented a lot with printed gearboxes, which had a number of problems. They broke, they had backlash in them, and they added weight, of course. But I needed this to get the smoother print, and also because just using the Bondtech gears directly, I found with this motor, to get the torque I needed, I had to run it at a relatively high current. The motor started getting hot, and then it started melting the filament as it went through, and melting the printed body of the extruder itself. So this solves all of those problems, and it's way lighter, and it's only one small thing. It doesn't break, and it doesn't have any backlash. You might wonder, is there not a downside? If I just rotate this, you can see the filaments rotating the back of the motor. How much torque does it actually apply to the filament for the filament to feed through rather than just rotate? The answer is not very much at all. So with minimal torque, it will push it through rather than rotate the filament. In fact, just the end of the filament being in the hot end and in that molten plastic is enough to provide enough back torque to stop this filament rotating if you get the edge just right on the bearings. And you may wonder what kind of filament it works with. Well, I tried it with PLA and PETG. I found it works really well with PLA. The PETG I've got is a little more grippy, and I haven't quite finished fine-tuning that, but RQ3 reports it works perfectly with that, and he's used it with a whole range of filaments, even TPU, and he says it works really well with all of them. The VDE100 is small and light. This one weighs in at 7 grams. My own one is even lighter at 5 grams. Better still, because it has such a low torque requirement, it can run off a very light motor. Here's a photo of one being driven by a NEMA 11 motor. The entire assembly weighs 37 grams. Finally, let's have a look at a disassembled, all the parts of RQ3's extruder, so you can see in more detail how it works and what it is that I'm targeting in making my own extruder. A CNC machined aluminium carrier with a grub screw in the side, 3 high precision shoulder screws with Belleville spring washers, and 3 extended inner race bearings. That one is a flanged bearing, and RQ3 has ground a knife edge out of the flange, cutting an edge both on the inner and the outer side of the flange. I found that challenging. It's pretty easy to grind the flange from this side, but to get in under there, not so easy. Okay, let's move on and talk about my version of the VDE extruder. I wanted to make this for the reason I've already mentioned, which is I wanted to be able to make one at home, wanted it to be something that anyone could make, and another reason as well, which is I wanted a higher cant angle. RQ3 made his with a 15-degree cant angle, and I wanted a slightly higher cant angle, which means that it feeds a little bit faster at the same motor speed. And the reason for that was simply that I'm running off a 12-volt system, and with the lower voltage, running the motor at the kind of speeds you need to run it at to get a decent feed rate at 15 degrees was tricky. So I wanted a slightly higher feed rate, a slightly less gearing ratio, a little bit more torque, and I wanted to see if that would work, and it turns out it works very well. Now, it's really simple. Mostly it's a printed part. The key questions which I had to explore, and as you can see, I've done quite a lot of exploring. If you look at this is just some of my experiments that I'm showing you now. The key question was grinding. How do you grind a symmetrical knife edge and get it really nice and symmetrical around the axis, so there's no flat spots, the cut, the bite between the knife edge and the filament is uniform all the way around the bearing, and how do you grind a symmetrical edge? So that was a key question. And how many knife edges, how many plain pressure bearings, where do you place the bearings? These are all a vast number of questions I've explored. And so, but the key question, one of the key questions is this knife edge. So let's move on and talk about that. I have worked out that the knife edge does need to be ground on both sides. I'll draw a cross section for you. If this is the flanged bearing, the flange needs grinding both on the inner and the outer edges. Otherwise, retraction and de-retraction happen at different rates. If you grind a chisel-shaped edge, then the filament cuts a different pitch, a coarser pitch in that direction than it does in that direction. It moves faster in that direction. I can only surmise because it's being given a little bit of a boost by that slanted edge. So this will not work. However, you can cheat. It turns out if you cut another chisel edge on another flanged bearing and you mount both of them on your extruder facing in opposite directions, then they balance out and retraction and de-retraction works. RQ3 already knew all about needing a double edge. He'd also found that retractions and de-retractions didn't work with the chiseled edge. But as I say, two chiseled edges facing in opposite directions solves this problem. I moved out to the shed to show you the actual using of a power tool to grind the edge. This is a sacrificial bearing. I initially ground it with a 30-degree included angle, so 90 degrees up the way, 60 degrees that way, leaving 30 degrees of edge. It was too thin and it broke. So this is a sacrificial bearing, and I'm going to use it to show you how to grind a 45-degree angle, chisel angle just on the outside of the bearing. This is a 5mm drill. The inner diameter of the inner race is 5 millimeters. It fits easily over the drill, and the outer race can turn freely. Trouble is, it can also slide up and down on the drill too easily. So a little bit of insulation tape over the end of the drill makes it just tight enough so that the bearing will sit on the drill nice and firmly, but the outer race turns freely. This is key. To grind this edge, it's got to be ground absolutely evenly, no flat spots. It's got to be ground at a 45 degree and the same amount of metal taken off around the entire circumference of the flange. That can only happen if the flange is rotating at the same time as the cutting edge is cutting. In this case, the cutting edge is sandpaper on the bottom of the sanding disc, and the thing that makes the flange rotate is, here's the trick, also the sandpaper. With the sanding disc, you could do this with the sanding belt as well. The sanding disc is moving, and you place this bearing nice and firmly, oriented just right against the sanding disc. The bearing will both rotate, and the sanding disc will take material off the bearing. I do that a little bit, and then I use my calipers to measure the edge. I took this down to 9.8 millimeters. No particular reason why it has to be 9.8. It's just that I've done experiments with larger, and then I needed to cut down smaller to change my experiment, and I've ended up with 9.8. Okay, close up. Place the set square against surfaces perpendicular to the cutting surface. Line the drill up with the edge of the set square. So that's now at 45 degrees. Once it's running, I'll press it gently against the sandpaper and check that I can see that the outer race of the bearing is rotating. If it isn't, I just adjust it slightly so that it is. And once I'm sure it's rotating, I can press it a bit harder. I find it doesn't really take much off if you can't see sparks, but if you can see sparks, it's taking it off fairly quickly. And so my start diameter. You can grind this down to pretty much any diameter you like, as long as there's an edge left, and then print the carrier to suit that. And in my design of the carrier, which I link below, that's a parameter that you can set in FreeCAD. But for this one, because I've already ground this before, it's presently it's at about a diameter of 9.9. So let's take it down to 9.8, and you see how it's done. Do keep stopping and checking. You can always take more off, but you can't put more back on. So let's see what it's at now. Measuring about 9.85. Very nearly there. It's about 9.83. I check it I rotate it several times and check it just to check that it's looking symmetrical. If it gets so it's not symmetrical, you need to start again with another bearing. Still a little bit of way to go. And that's pretty much it. And that's how it's done. I also found, when I assembled the thing, that the plain bearings, with this diameter of bearing, I'm going to try a new experiment with even smaller bearings, but with this diameter you can just get the knife edge catching on the corners of the plain bearings. And you can simply use the same trick, just to grind off a slight 45-degree angle. If you imagine this were a plain bearing and that was its edge, you can grind a slight 45-degree angle off the corner of the plain bearings to solve that problem. Once you've ground your bearings, this is how you mount them on the carrier, which you'll obviously need to print out. There are two MF95ZZ bearings with chisel edges ground on them, and one MR105ZZ pressure bearing. I haven't shown the screws, but you'll need to screw some M3 screws in. Make sure the heads of the M3 screws are small enough so that they only press on the inner race of the bearings. And you'll also notice, if you look carefully, that the posts that the bearings are mounted on, the printed posts, are a little bit less, about 0.5 millimeter less high than the inner race of the bearing themselves. That leaves space for the head of the screw to actually press firmly against the inner race of the bearing. Once you've done that, it's merely a press fit onto the shaft of the stepper motor. And a press fit works because of the lack of, there's just really not that much torque involved. And so I find that the easiest way to connect it to the shaft of the stepper motor. So, does it work? That's the million-dollar question. The answer is yes, it does. Here is a half-scale benchy I printed with it. Here's a close-up. The carrier itself was printed with a variation on this extruder. In fact, this carrier was printed with one that had ever so slightly less bite between the knife edge and the filament. And happily, I also had people in my life who have things that break, who asked me to fix them. And conveniently, my wife had recently approached me and said, "This spade needs a new handle. Do you think you could print one?" Well, let's find out. This is the beginning of the print of the spade handle using my very latest version of my VDE carrier. And as you can see, it's printing fine. I'll let you watch some shots as it goes through. Here's the final product, and here it is on the spade itself. These are just a few examples. I've been printing for a couple of months now with this extruder and printed many prints, and I'm very happy with them. And are there any caveats? There is one. It's not the fastest extruder in the world. I've already mentioned the advantage of the leverage, which is brilliant, but it does mean the motor needs to turn faster. If you're running off a 12-volt system, then your top speed is limited. So that's one thing. And the other thing I've found is all extruders experience a certain amount of compression. The faster you extrude, the greater the extrusion multiplier that you need to extrude the same amount of filament. I found that the thread pitch that this cuts in the filament contracts as you extrude faster. And I wouldn't want to extrude any faster than about 3 millimeters per second with this, because otherwise that retraction starts having a noticeable effect. Is it a problem? Well, it will only affect infill. We don't extrude perimeters at that kind of speed anyway, and so one can simply compensate for it by specifying a larger amount of infill. I'm considering perhaps writing a post-processor for the G code that will fix it, or possibly even submitting a patch to Marlin that will fix it. But that's what we got for now. I haven't been able to beat the compression. Most of the variations I've tried were attempting to do that. Would I change anything? Yes, perhaps I'd pick different bearings. I've been looking at the MF85ZZ, which is a millimeter less in diameter. That would reduce the likelihood of interference between the knife edges and the plain bearing, and would also shave 0.5 millimeter off the height of the thing, and probably less than a gram off the weight. But hey, less weight is faster moving printhead. And I've also worked out something else that RQ3 had already worked out, which is how to mount it on your printer. It's really important to have quick access to remove the extruder, because it's really not great at retracting filament that's been in the hot end. That blob you get on the end jams in the end of the extruder. So you need to be able to take the extruder off, cut the end off, and then remove the filament if you want to do a filament change. This is really fantastic, actually. Being able to quick remove the extruder means that I have brilliant access in, and if there ever is a filament jam, I can easily get in and deal with it. Or if I need to clean the nozzle, I've got direct access right down there. I can stick a needle or what have you down the hole to clean the nozzle. Anyway, this mounts simply by having two little studs screwed into the screw mounting holes here, which go into screws over there, into holes. That prevents the rotation, and a clip with a hole in the middle for the filament sits on top. This entire mounting is designed to work on a Prusa machine, so you can actually replace the Prusa extruder with this complete thing. It just bolts on in exactly the same place, and your Prusa machine suddenly has a VDE extruder. Okay, I'm done. That's my make-it-home version of the VDE100 extruder. Have a look below if you want a link to all my project files so you can make one of your own. I'll include an STL file sized for an MF95ZZ bearing cut with a 9.5 millimeter diameter knife edge, or you can make your own, whatever size you want, just by adjusting the parameters in the free CAD file. There's also the models for building a mount for a Prusa i3 style printer, and I've also included a device that you can bolt onto a motor which will center a drill, so that you can, I use that to help me drill a straight hole down the center of my drill shaft. Hope you enjoy.